Now, the hypothesis for this experiment is that the angle the mass is released from in a pendulum motion will influence the time period the mass would go for one round of oscillation. Meaning, the time period will be dependent on the angle the mass is released from. And what I think the prediction would be is that the shorter the angle, the less time it takes for one round of oscillation to occur. And we're going to put that into the test right now. All right, welcome to the potato pendulum experiment, where we will be conducting an experiment here to determine as to whether the initial or the angulation of a mass released in a pendulum motion would depend on, is the time period for each oscillation for the mass hung dependent on the angle said mass is released from. And so right here we have our setup where a potato is hanging using a light string from a stable apparatus here, and the length that we have here would be 18 centimeters, and all the data entries will be demonstrated in the Google Sheet that will be uploaded onto Blackboard and attached with the Gmail that will be sent. And so what we're going to be doing here is, what I did initially was to set up the length here to be 18 centimeters, and now we're going to release it from a short angle first, and I will have time recorded for how long 10 oscillations have taken place. And so we will start in 3, 2, 1, go. 2, 3, 4, 5, 6, 7, 8, 9, 10. And the time here would be for 8, let's see here, 8.83 seconds. And now the second attempt will be from a greater angle, and the release will occur in 3, 2, 1, go. 1, 10. And that would result in 9.43 seconds. Now, the second length here, let's aim for a greater length than 18 centimeters, which would be approximately around 36. So double the initial length. I have here my measuring tape looking like a tailor. That will help with getting the right measurement of length. We will have it further down. Okay, and now at 36 centimeters, we will start from a short angle. Going at 3, 2, 1, go. 2, 3, 4, 5, 6, 7, 8, 9, and 10. And that is 12.27 seconds. And now from a greater angle, we will release in 3, 2, 1, go. We gotta repeat this. So 3, 2, 1, go. 1, 2, So 1, 2, 3, go. 1, 2, 3, 4, 5, 6. Keeps knocking. Let's try one more time here. Go like this now. Try and keep it as stable as possible. Right here. And 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That is 12.11. Okay. And for the third case, we'll have the length set at 45 centimeters. And I'm going to be releasing it from the short angle first. We will go ahead and start timing in 3, 2, 1, go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right. And time taken was 14.12 seconds. And now releasing it from a greater angle in 3, 2, 1, go. 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 14.36 seconds. All right. As shown here in the table that we've used to record our data in, the lengths here are set on this side of the table or on this column, and we have them converted into meters. Here's the time taken that we have recorded for 10 oscillations of the mass, and the time period recorded in seconds are shown right here in this column highlighted in gray. Now, as shown here, angle 1 is the shorter angle and angle 2 would be the greater angle for all three cases. And it's the hypothesis that we stated earlier is true given the data that we have entered here. It's been supported. This data supports our hypothesis that the time period is dependent on the angle the mass is released from, and the shorter or the smaller the angle is, the less time is taken for the mass to travel in one oscillation period. And for further calculations, we have determined the acceleration here for the mass and the percent difference. And so the percent difference for the shorter angle is less in all cases than the greater angle or angle number 2. Hence, our experiment is concluded and the hypothesis that we decided on is true.